First of all, with respect to your final project, on my webpage you will find a list of papers, manuscripts that are somehow related to the course. These are published in journals, so they are like professional articles. For next lesson, next Sunday, that's the last lesson, please go over that list and choose out of that list one project that you want to summarize. The idea is the following. You read this article, you hopefully understand it, and then you summarize it, and you explain what is written there. It's a little bit tricky. You should explain it in such a way that I understand that you understood it. Which means we don't copy what's in the article, you try to explain it. When I say I want to see that you understand, it means the following. Let's say there is some article, and in it there is some simple simulation. You repeat the simulation, maybe with some different parameters, and say, hey, look, this happens, this happens, this happens. This for me is considered a good summary, in the sense that you did something, you defined some mini project, not a mini project, a mini question. You solved something and you showed me that you can change parameters and find something not new, but something slightly different than what is in the paper. So to do that, you should be ready for next lesson. In next lesson, once you have your paper, your favorite paper that you want to do this project, then you can discuss with me next lesson. And let's see what is your plan and what is your idea. Now, in principle, a few people asked to do projects which are not on this list. I don't object to this. But this is very difficult because these specific papers that I was giving you were specifically chosen such that you can really understand them quite easily and really develop the analytics if it's analytical, or do some simple numerics. But if you want to, or if you have some good idea of something very much related to the course, I'm not against it in principle. So if you have a paper published in Physical Review, not necessarily letters, actually, usually not a letter, and letter is not good because it's too short, you will not understand. But let's say in Physical Review E or some journal that there's a paper with some explanations in it, then, okay, if you are interested and you know of one and you think it's related, so you need to tell me next week. Or even before next week, to come to my office to take advice, and then I might consider it as a possible project. Okay? In addition to this summary of one article, there is also a project where you simply solve some exercises. This is like a usual exercise, but it's slightly longer. So that would be also part of your grade. Okay, so be prepared for next week and we will discuss it. Now, what I want to do today is I'm going to discuss more recent applications of some of the ideas that were developed in this course. It will be more from the bird's eye view, which means I'll give a presentation on the with this projector, right? So it will be like a colloquium type of talk, but please ask me questions. The goal will not be to go into the mathematical details so much, but that you'll just see some experiments that are related, and B, you'll see how the theory was really pushed forward maybe in the last 10 years or so, or a bit more, 15 years or so. So one of the things that came out of all these random walks with these long-tail distributions of waiting time. So remember what was the history. We had these very old experiments that were analyzed by Sharon Montrol in Xerox company. And then they were looking at some semiconductor which was very disordered semiconductor. They had a flash of light, and then you had electrons moving in the system, and they were just looking at the current. And this is, of course, in some sense, an ensemble average experiment. When you have current, what does it mean, a current? You have many, many electrons. You are all of them moving together, and you are measuring the average current. On the other hand, if you look at one particle, of course, you cannot look at one electron. That's a big problem today. But you can look at one, for example, a single Brownian particle, or a single molecule diffusing in a cell, or a single molecule in a disordered material. In the last 20 years, single molecules were followed in really a lot of experiments. You'll see why soon. So then you have one trajectory. So in ensemble measurements, let's say of diffusion, you have, let's say, Brownian motion. You have some path in space. You have particle 1, then you have particle 2, and you have many copies of this. You have n particles in your system. For example, if I drop some ink in water, it spreads out, but what is spreading? Many particles that are atoms of the ink, molecules of the ink, right? So here we look at the density of the particles. So let us assume these are many, many trajectories, all starting on the origin. And even further, you cannot distinguish between particle 1, particle 2, particle 3. You just have, you see the density spreading out. So you will see in the experiment something like this, for example. And then after some time, it will be spread. And then it will be even more spreader, etc., etc. And you will see the density of particles, and we calculated such densities. If it's Brownian motion, it's a Gaussian, and if it's not Brownian motion, okay. There are some anomalies here, but this is the density that you are calculating. And in particular, what you measure, this is the most common measurement, is the mean square displacement at time t. So you see here, this is roughly the size of this packet. It's small at short times because all of them started at the origin, then it became bigger, and then it became bigger and bigger and bigger because you are some diffusive process. This could be linear in time, then we call it normal, or it can be anomalous, and then we call it subdiffusion or superdiffusion. Subdiffusion if it's slower than linear in time, superdiffusion if it's faster. Okay, all this is great. You can do other ensemble measurements which are very traditional in statistical physics. For example, let us say you have a harmonic oscillator and you have many particles inside, or let us start with one particle. So what I'm plotting here is a trajectory in an harmonic oscillator. What is this? You take a particle, you take some, let's say a polymer, you put a bead at the end of the polymer and you put it in water, and then the polymer is like a spring. It's pulling this bead that is on the end, and it's moving because it's in water, and there is some temperature T. So this is like Brownian motion, but inside the potential field. This will be described in the limit. We talked about this a little bit with the Fokker-Planck equation. If there is no memory, if you are close to thermal equilibrium, etc., etc. But even before that, you can say, okay, what do I measure? I measure here, for example, the variance. And I can measure the variance in equilibrium. In equilibrium means at the long time limit. And you know, for example, from equipartition, from basics of statistical physics, that half m omega squared omega is the frequency of this oscillator. So this is simply equal, according to equipartition, to K Boltzmann T over 2. So this energy is simply the energy temperature. So what do you do in a measurement? You have many particles, let's say, or you can do it one particle at a time, and you do it many times. And then in equilibrium, you have some density, which is Boltzmann's law, V of x over t. There's a normalization. And then because this is a parabola, this is a Gaussian. Very simple. And then you can measure in equilibrium, you can measure x squared average in equilibrium. You don't need any dynamics. You simply calculate x squared e to the minus vx t dx, and you normalize the partition function. So here I have normalization. Z is just the integral over the over the Boltzmann factor. This you all know from StatMech. Here K Boltzmann is 1 dx. This is the partition function. On the other hand, you can do a time average. When you measure. So let's say you have only one molecule, one such particle in the harmonic oscillator. So you have only one trajectory. Then you define a procedure of time averages. For example, for this observable, you can define x squared bar. And the bar means a time average, not an ensemble average. So again, ensemble average, you collect many particles at a given time t. You take the time t to be long, and then you get in equilibrium, you get some number. Thermal equilibrium, all is nice. But what is the time average? You can define it like this. You take an integral x squared t dt, and then we divide it by t, and then usually people would like to take the limit t to infinity. What does this mean? We take snapshots of the position of the particle in this well, and we take it. You can do it stroboscopically, or you can do it. You don't really need to do the integral. You take it, let's say, at this time. Take it at another time, and another time, and another time, and then you actually, this integral is a sum of x squared. A sum of x squared divided by the number of points. So what is the whole idea of ergodicity? First of all, what is the claim of ergodicity? Is that this is equal to this. You can replace this time average with the ensemble average. If you can do that, you call the process ergodic, as I think all of you know. Now, what is the idea of ergodicity in this very simple case is the following. Let's say I sample this let's say I have an experiment that runs for 1 billion years. The characteristic time scale inside here is 1 second, let's say. And then I sample every, let's say, week or something like that. And I find the position of the particle. Because the time between sampling is much bigger than the memory of this system, then each time that I sample from an independent realization. So it's the same as having an ensemble at one time, and then once I find the particle here, other time I find the particle there, etc., etc. Because once the measurement time is long compared to the typical time scale of relaxation, it doesn't matter that you are looking at one system. You are looking at many systems. It's the same thing. This is the main idea of statistical physics, actually, because it said in many experiments, for example, you want to measure pressure, or you want to measure actually temperature, whatever you measure, usually in many cases at least, you measure the time average. And that is a super awkward procedure, because you see this function here, x squared t in this example, is fluctuating like mad. It's a very complicated function, this function, along the trajectory. So instead of doing this awkward time average, what people are doing most of the time, they are calculating the ensemble average. And this, we have rules of statistical physics how to do it if you're in equilibrium, etc. So this is very nice. But already here we see something. We see that we said there is a characteristic time, TC I'm going to call it. TC is C is for correlation. This is the time where the particle loses its memory. After some time, it depends on the relaxations inside this oscillator in this example. And what is the physical meaning of taking time to infinity? It simply means that T is much, much bigger than TC. In practical world, You go to the lab, you have some fluctuating quantity, it has some correlation time, but you measure for time much bigger than the correlation time, and this process is also stationary. Then you can very safely replace this time average with an ensemble average, and you're very happy. But immediately you understand, if you understood what I was talking to you in the last previous weeks, I mean, in our systems, when you have anomalous diffusion, we have this power law waiting time. So if you have a concept like psi of tau, the time between jumps, alpha less than 1, then the average time is infinite. And this means that this TC is infinite. So you can intuitively understand that if you have these power law waiting times, then you want to do a time average in your laboratory, and then you should do it for a long time. But what is long time? The average time between jumps is infinite. So no matter how long you measure, at least in principle, you are never going to satisfy this. And that means that if you have these power law waiting times in your dynamics, you don't have ergodicity, and then all statistical mechanics in equilibrium, I mean, you put it to the trash. It's not working. Because you have no time scale. Time averages are not equal to ensemble averages in general. So here, this is found, you see, so the general idea is that ergodicity and statistical mechanics is not holding when you have these long-tailed waiting times, and you need to replace statistical physics with something new. The new concept is called something called weak ergodicity breaking. And this concept was introduced by Jean-Philippe Bouchot maybe 25 years ago, or something like that, in the context of glasses already. Glasses, what I mean by glasses, these are spin glasses. Let's call them complicated system, where he was looking at correlation functions of magnetization, actually, of a macroscopical system. And these correlation functions were not depending on the time difference, but actually on the ratio on 2 times of observation. While this concept that if you have these power law waiting times and they diverge, then you will not have ergodicity, weak ergodicity, because in weak ergodicity breaking. The big, at least from my point of view, the big breakthrough came when people were looking actually at single particles and then doing time averages and saying, oh my God, they don't converge to anything, they don't go to the ensemble average, what's going on? And that was an interesting period in my life, at least, where we could apply this weak ergodicity breaking concept to many systems and formulate the theory when you perform these time averages. So this will be I'll soon discuss this. This will be the topic. The theory is rather developed because you see, going back to Brownian particles, what I have here is I measure mean square displacement that grows linearly in time. This is a system out of equilibrium, again, because you are going like T. On the other hand, you have equilibrium systems where you have this confining well. Physicists like to work in a box. So this is equilibrium, this is non-equilibrium, because this depends on time. Again, equilibrium and non-equilibrium, already for Brownian particle with no boundaries, or a Brownian particle which is bounded by a potential or by some walls or whatever. So before starting, I want to explain also what do I mean ergodicity when you have this diffusion. So a very simple question. Let's say you have a particle in water, and you have only one trajectory. How do you measure the diffusion constant? Of course, this is nothing new. This was measured by Perrin when he got the Nobel Prize on Brownian motion. But the technique is very simple. You don't do an ensemble average. You don't look at many particles. You look at one particle. How will you then estimate the diffusion constant? So again, so this is your Brownian particle, no bulk, no boundaries. And I want to estimate diffusion constant from this trajectory. Again, I performed an operation which is based on the idea of ergodicity. Then I defined what I will call later delta squared average. Again, it's a time average. And this is defined like this. You take, which depends on something I call delta. Delta is called the lag time. So the experiments take the trajectory. I'll do it in one dimension, but it's the same thing. And he or she averages from time 0 to time t minus delta. T is the measurement time. And it's much bigger than this lag time. This lag time is like when we have an ensemble, usually we have x squared. We usually write it as 2 dt. It's a bit confusing. This delta and this t are the same thing, actually. So how do you take your trajectory, and then you define x t prime, plus delta minus x t prime squared dt prime, and you divide by t minus delta. So what is this thing? It's very simple. Along your trajectory, you take 2 points in time, t prime plus delta minus these 2 points. So you take 2 points, let's say here, this was on time t prime, and then here, t prime plus delta, you were here. Then you take the square of the difference. Then you move along the trajectory, and you sum up all these contributions. This is the meaning of the integral. Of course, in real life, you can sample. You take time t, time some t2, t3, t4, and then you just turn this integral into a summation. And then what is this guy? This guy is, you see, because of the square, this is the mean square displacement. This is the how much you moved between time t prime and t prime plus delta. And then you sum it, which means you average it. So this, if you have Brownian motion, this goes in the limit where t is very big and delta is much smaller than delta to 2d delta. And what is the nice, but maybe trivial, I don't know. I mean, you take one trajectory only, and you get out the diffusion constant. Maybe because you were trained as ergodic, everyone says ergodic, so you believe it's trivial. But now we will show that it's not the case when you have the more interesting case. So instead of taking many particles, like a packet of particles which is spreading, and measuring how wide they are, you take one particle, and then you get this diffusion constant from a single particle. So I would say this is very old and trivial, but maybe for you it's new, so okay, maybe you need a little bit of time to think, what is this operation doing? But the fact that this guy, so we can summarize, if you have Brownian motion, the long time average is x squared at time delta. This means ergodicity, because here you average over many particles at some given time delta. Here you average over one path at a given delta. And this is ergodicity for the evaluation of the diffusion constant of a single individual particle. Of course, the interesting part is that it doesn't work. So what I'm going to start with, more or less, is the simplest system is that we know. And when I say simplest system, I'm a bit lying. I mean, what does it mean, simplest system? The simplest system that exhibit weak ergodicity braking are so-called blinking quantum dots. And it's simple because these blinking quantum dots have only two states. It's like a spin, up and down. Here we have also two states. So I will discuss this. Now, quantum dots were considered like a system that interests people because of nanotechnology. I'll soon explain why. It was like investigated by hundreds of laboratories. It was a very prominent system in nanotechnology 15 years or so, maybe now less. And I'll explain again why. But this comes really from the field of nanotechnology, and from most of the point of view of most people, all this ergodicity braking is a pain that they suffer from it tremendously. But of course, I enjoy it very much. So you'll see why soon. And another system that I will analyze briefly are diffusion of molecules in the cell. So again, this is a field that people got Nobel Prize for single molecule tracking a few years back. W.E. Morner, for example. The ability to follow one molecule at a time is something totally untrivial in when the molecule is embedded in a condensed matter environment. Even more when it's in the cell. It's a great achievement over the last 30 years or so, and the last, I would say, 15 years. Okay, 15 years ago it was popular. Now I think it's starting already to decline. But this was very important because imagine, let's say, for example, you have your DNA in your cell. And there's some messenger RNA, it's coming and attaching to it. And then it's leaving the cell. You want to follow this messenger RNA in order to know how fast this messenger RNA moves. If it moves fast or slow, this will determine your reactions that make your life possible. So again, this is a gigantic field. And of course, let's say you have a cell of some beast, and then you have, let's say, one molecule. What is the molecule? Could be many things. It could be some messenger RNA. I will discuss some experiments soon. There are many, many problems here. There are many nice experiments by Yuval Garini, for example, on not exactly in the cell, but in the nucleus of the cell. But there are hundreds of experiments like this. It's nothing. I mean, it's a really exciting field over the past 20 years or so. And then when you have one molecule in the cell, well, it does something like this. Some junk like that. It's moving, and it's moving not deterministically. This is obvious. It's much more complicated than what I'm going to present here because I don't have time. There are different types of motion. Some of them are active. So then you can see kind of a particle just moving along at some very nearly deterministic trajectory and then jiggling. There are other particles which are more or less passive that look like Brownian motion. Other particles that do anomalous diffusion, because it all depends on the size, on what stage this cell exists, what is the cell, etc., etc. So when I say the cell, for physicists, there's one cell, your cell, but it's not true. Because you have different types of cells, you have different molecules inside the cell. It's very, very big. It's very big field, I would say, out of which many of the processes are not ergodic at all, and many of them are not normal diffusion, but anomalous diffusion. And governments were eager to invest money into this because, of course, they want to apply this eventually for medicine. Because if you know how fast your molecules move in the cell, what controls their movement, maybe another 20 or 30 years, people will be able to control it better and understand better all kinds of disease. So this is a tons of money inside. But we physicists, we just more or less follow it. And the physicists, also chemists, I would say, had something, a tool that the biologists didn't have. It's also true the opposite. What is the tool? There are two tools. One big one and one small one, I would say. The big tool was this beautiful optics that enabled one to follow one molecule at a time. This is advances. This is the best microscopy people are able to do. And again, in this university, Yuval Garini is an example. And the second, smaller maybe, impact was the analysis of what are these trajectories at all. Are they Brownian? Are they ergodic, non-ergodic? Of course, biologists, they care about other things because they care about some biological function. And I would say that the two communities are not discussing so well among themselves. Now, you see here, we have blinking quantum dots. This is nanotechnology, diffusion of molecules in the cell. This is biotechnology. And then we get non-ergodicity. In my opinion, this is just pure chance. We have here systems which are complicated somehow. They are popular because of technology. And then hundreds of laboratories investigate them. And then out of hundreds of laboratories, 99% of them find anomalous diffusion and non-ergodicity. But if you go to other systems which are not popular, but they are in disordered state, you will see similar behaviors. So the fact that we are in these regimes is just kind of coincidence. It's not exactly coincidence, it's simply you follow a wave of science that follows the governments that give money on these systems but not on others. And then you discover on these systems, you discover weak ergodicity breaking and everything that you were taught about ergodicity is simply wrong. But again, I don't think it's special at all. Doesn't work. Of course not. אני יודע, זה כמו אדום. כן, משהו. למה? זה ירידה. אוקיי, sometime. Sure. People can follow a single molecule in the cell, but we don't have a projection at all. לא, אפשר, אבל... זה לא נראה לי... now there's no light. How do I know it's light and not a reflection? It's red and not green. Oh, it's green. ואיך מעבירים את זה? אוקיי, תקראו לה, אולי I can find here. Sorry. Okay. Okay, so by the way, these are two references of popular articles. Physics Today is a super popular article that we wrote, one of them on the single molecules and one of the blinking quantum dots. So in principle, you can take these type of articles to summarize, but it's much better to go to the references inside these. For example, these two fields, if you're two article summaries, if you are interested. So let me again. Just repeat myself. This is just the motion of ergodicity. You have a particle with some spring. You can perform a time average. This is this time average. For example, on the average position, which is a very complicated. This is a functional of the stochastic path. You take a time average. You take the limit of long times. Or you can take an ensemble average. And the ensemble average means that we have some density. This density you can measure, or you can calculate if you have a basic theory like Boltzmann-Gibbs. And then the time average and the ensemble average are the same. This is just the ordinary statistical mechanics idea. And then if you have a Brownian particle in, let's say, 2 dimensions, then you can take the square of this, as I just now said. And then if you take this trajectory to be long enough, it's a very stochastic trajectory. So again, this variable here inside the integral is random, but you average it over long enough time, and then you get the diffusion constant out of it. This is usual philosophy, but now we want to discuss something a bit different. And the first example is related to these blinking quantum dots. So to understand the blinking quantum dots a little bit, we need to describe a little bit what is a quantum jump. So the quantum jump is really something fundamental. It was envisioned by Bohr. So you have a hydrogen atom, and then you have an energy state, and then boom, you jump from, let's say, from one excited state to a ground state, and let's say you emit a photon. So this is the most basic process, one of the most basic processes in physics. The idea is that you have discrete levels, and then by emission or decay, you can jump between states. So the philosophy was there from the times of the beginning of quantum mechanics, and this is the so-called quantum jump. But now, this is old. This is 40 years old. Now people were asking themselves, there was a beautiful colloquium last week that describes this, how can we, in the laboratory, see a quantum jump? Very legitimate question. And the first issue to understand, it's a very simple point of view, to see a quantum jump, you need to look at one atom or one ion or one molecule at a time. You cannot look at many of them together. What is a jump? If I jump, you see it. But if many guys do the jumps at random times, it'll be very difficult to see it. So, maybe I'll turn off the slides. Is it better? So, here is an example of how you see a quantum jump. You have a molecule or atom which has actually 3 states. This is called a V shape. You have a ground state, and you have one excited state, and then there's another excited state. The idea is you pump the system with what we call a weak transition, and here with a strong transition. This means you have 2 laser fields, but this laser field is very, very weak, or this motion is very, this transition from here to here is very rare. And what you get out of these experiments is photons. Photons are coming out at you. Because you excite it, and then this wiggly curve is a photon coming out. Another example, which is actually easier to understand, is this very, very common. Every molecule, like every organic molecule that you put in a condensed matter environment or in a gas phase, will have this structure of energy levels. It has in it a ground state, as you know. Think about this as a ground state. Then you have something called a singlet excited state, and here we have a triplet excited state. So the idea is the following. Let's say you come with a resonance laser and you come and you excite it here. These upper energy levels are actually vibrations. So there is a small band here, but you can think about this level as one unique level. And you come with a laser, it's in the ground state, you excite it up here. What will happen? You will emit a photon and it will come down here. You again excite it will come down. Excite it, come down. The time between emission of photons in this type of experiments is roughly 10 to the minus 9 seconds, roughly a nanosecond. But in this system, we also have this triplet state. And this triplet state, in a rare occasion, the system will go from the excited state, this excited state, it will go here. Let's say you excite, it emits a photon, excite, it emits a photon, you get out 10,000 photons, and then randomly, the system jumps into here. This jump is the quantum jump that we can measure. The point is the following. This state is long-lived. Let's say the time it will take it to decay to the ground state, let's say, is 10 to the minus 3 seconds, or even a second, or something like that. So what will happen? In this system, you'll go up, boom, emit a photon. So you will see tuck, 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 many photons, many photons, and then suddenly you'll go into this state. And in this state, you don't emit a photon, maybe eventually like this, and this state will live for long enough. Why does this state live long compared to this emission? Is because this is a triplet state, and there is something called a forbidden transition. Well, a forbidden transition is that in perturbation theory, the transition from here to here is very weak, very rare. It doesn't happen often because of the symmetry of the wave function in this state. I'm not going into that physics. But the point is that when it goes up here, you are in state on. And then you have many photons. So what we are plotting here is the number of photons versus time. So you have a gun, you emit many photons, tuck, 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 tuck. You don't measure all of them. And then you are in state on. And then you go into the triplet state, and you see here the scale is roughly a second. Of course, there's noise still in this experiment. And then you go in state on again, and then off, on, off, on, off, on. The off states are again these triplet states. And this is the jump. You go from on to off, boom, you did a quantum jump from here to here. Now, first of all, imagine that you looked not at one of these molecules or those molecules, it's the same thing. But let's say you had in your laboratory an Avogadro number of these molecules. These quantum jumps are all made at random times. So what would you see when you look at an ensemble, many of them? You would add many of these processes, and these decay times, these jump times are random, and then what you will see is just the counts per bin. Again, what is these counts per bin? These are the number of photons, let's say, for 1 millisecond. So this is essentially, this is the current. It's the current of photons, of fluorescence photons coming out of the system. These fluorescence photons that come out when you jump up here. Okay, so people were very excited 40 years ago or 30 years ago. We can measure the quantum jump. Now, and this is done in many systems, people observe the quantum jump. This is in some sense, it's like a renewal process, because you see you're on, off. There is some statistics of on times and statistics of off times. And if you follow usual traditional quantum mechanics and you calculate them with second order perturbation theory, the distribution of the on times and the distribution of the off times, so these are the times that you are just going up and down and the time that you stay here, they should follow exponential distributions. So you see it here. So there is a typical scale, which is this scale. You see it with the eye, or at least I can see it. Sometimes they have some fluctuations. But typically, you jump after, let's say, this is a second, so after 1/10 of the second you're on, then you are a little bit more off. And you see it here in this distribution. This is the PDF, the probability density function of the on. So you see the on is short. So it's exponential. This is a log scale. It's exponentially distributed. This is also exponentially distributed, more or less. And this is the basic thing. It's new for you, but from my point of view, it's already old. This is the classical picture. Of course, if I will perform a time average over long enough time, over, let's say, the intensity, I would get actually the time integral over the intensity. These are this rate of photons coming out is the total number of photons coming out. If I make it long enough, I'll get some time average, and this will converge in distribution to the ensemble average, which is the average of the intensities of many identical systems. So you can take, in principle, this is even older stuff, you can take this molecule, not one, but let's say Avogadro number, and then you can do this experiment, and then you can measure the average intensity coming out of a huge number of molecules. This was done 100 years ago. You can take the time, only one, but long enough. And then when you average over the intensity over time, it will be the same as the average over the ensemble. Why? Because you see the relaxations, in this case the on and off time distribution, are both exponential. There is a typical time scale, roughly 0.1 seconds in this experiment. If you measure for much longer than 0.1, you are ergodic, more or less. Okay, trivial. But then came a system which is different. And this is the quantum dots. This is the exciting news. First of all, what is a quantum dot? So a quantum dot is, you take some semiconductor, for example, cadmium selenide, and you make it, in this example, it's 5 nanometers, but let's say it's 2 nanometers or so. And importantly, you embed it in a matrix. So they prepare a matrix made of material B. The matrix is cold, and you prepare this thing. How do they do it? For example, here, I'm not going to go into full detail, but you have here, this is the core. This is the cadmium selenide. It has thousands of atoms inside, but it's, again, 2 nanometers. Around it, you have a shell. And around it, you see these small hairy things. These are all kinds of junk polymers, meaning the system is embedded in a disordered system. It's very important, actually. It's not a clean, it's not like a one atom floating in the air. It's interacting with an environment in a complicated way. What is the goal of this, let's say, this shell? So this is cadmium selenide. Let's say this is zinc sulfide, some other material. The goal of this shell is very simple. You want to make here a particle inside the box. You remember the quantum mechanics course, you have a particle in a box. This is a physical realization of the particle in the box, but instead of a box, you have something like a small sphere. And this shell, the aim of the shell is that if you excite here, let's say with a laser, you excite here an electron, it will not go outside. But already this picture you see, I plotted in a schematic way, you see there is a problem here. It's not exactly a sphere. Why? Because the lattice structure of this guy and the atoms around here are different. You cannot make a perfect sphere. You cannot make a perfect shell. This is something that chemists are working tremendously hard, how to make a perfect sphere, a perfect shell, such that an electron will not go outside. Super, super difficult. People in laboratories invest their life to do that, and they are not really capable of making something like a particle in a box. So first of all, why do we call them quantum dots? It's because of their size. The size is 2 nanometers, which means the energy level of an electron excited here will be quantized like a particle in a box. It's not a box, it's a sphere, but it's more or less, it's quantized. And people, again, for 30 years, they measured this. How did they measure? They measured with ensemble measurements, first of all, with spectroscopy. What are the measurements? You take some solution. This is different than this. This is the modern experiment. First, they took some solution, and they threw in billions of quantum dots here, 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 here. And then they could change, the chemists could change the size of the quantum dot. It's very difficult. But that was done already 40 years or so ago. And then they see what you all know from quantum mechanics. If you control the size, you control the wavelength of the emitted light, and then you can change the size. You can have red, yellow, green. Wow, this is wonderful. I could take paint and I could paint and I'll get the same thing. But they did it quantum mechanically by changing the size of the quantum dot. Again, in solutions, they are not measuring one at a time, so they see nothing. I mean, they see something. They see the energy levels. These work perfectly. Quantum mechanics works very nice in that sense of energy levels. So a lot of work modifying the size. This is an example. So these are the wavelengths, and you have different materials, and you can change the size of the quantum dot, and then you can change the emission color. And everyone was happy. Quantum mechanics works perfectly. Everything is good. More or less perfectly, I mean. And then people were able, that was, let's say, 20 years ago or so, they took one quantum dot and put it on a matrix. Again, all this is not trivial. And put it at very cold temperatures, let's say 2 Kelvin. And then they look at the intensity of photons versus time. This is for 1 hour. So what is the experiment? You have one quantum dot, you have a laser field. The laser field is a continuous wave laser field. It's exciting it, and then it emits photons. So this is the current of photons versus time. Exactly like the experiment I just showed you. So you remember, if you work on one molecule, you have on, off, blinking. It looks the same. Well, it doesn't, but if you are really blind, it looks the same. You have a quantum jump. You have on, off, off. But then you see with your eye, it's not difficult to see, that this is very different than the previous system. And you see with your eye, if you have a good eye, that this is a continuous time random walk in some sense. You see here the fractal nature of this blinking quantum dot, and this is simply unbelievable because all these power laws that Cheryl Montrol were talking about, they were kind of some kind of you average over many, and here you have these power laws, but one smaller system, 2 nanometer size. So this disorder or these weird effects happen on the very small scale, without averaging. And how do I see these that this is a fractal and these are power laws with my eye? Of course, I need to measure. This is easy. You see here, let's look at the off. You see here there's a small off, maybe here a small, and then you see maybe twice as big as what you have here. And then you have another one, and this guy is twice as big as this one. And then, okay, again some small ones, and then maybe this is bigger, this is twice as big as this. And then if this is the next one, then this guy is twice as big as or 3 times. And then you have many, many blinkings. And then, oh my God, you have another one, and then another one blinking. Another one, etc. What do you see here? You see with your eyes that the off times at least, but also the on times, you see very long off times, they don't have a typical scale. It's not like, let's say, all the on times and all the off times are roughly, let's say, 1 second plus minus 1. Okay? No. You see here short and very long. And as time goes by, these off times become bigger and bigger. At least to the naked eye, that's what it seems. So that's why we are going to analyze them with this waiting time distribution concept. How do you do that? You take your data, not from one quantum dot, but sometimes from one, sometimes from many. I'm not going into these details. And you define a threshold. This is this line. And then you say everything which is up here, on. Everything which is below this line, off. And then you plot the distribution of these on and off times. And you get what you get. I wouldn't be talking to you if you would get exponential, because that would be like the old theory. I'll come back to this later, but what you get is power laws. So this is example, this is experimental data. So you define the distribution, I call it psi here, distribution of the on times and distribution of the off times. So the off times are these crosses and the on times are these circles. And then you plot it, as you know, on a log-log scale. So if you have something straight on a log-log scale, it means that it is a power law. And from this slope, I can determine this alpha. So what do you see? You see it's very good power law. And look, it works really nice from roughly, this is order 1 till order, I would say 10 to the minus 4. So this is 5 orders of magnitude. And this is also pretty long. I mean, 3 orders of magnitude. Now, if you have a good eye, you can say, oh, this guy is going down. So maybe there is a cutoff on the on times. So what it turns out that when temperature is small and when the laser intensity is weak, then it's power law nearly forever. Or to put it differently, let's ask the question, let's say it's not really a power law, but if you wait 2 billion years, there is a cutoff. Who cares about the cutoff? But if there is a cutoff, let's say eventually it will go to something else, we don't care about it. Why? Because this cutoff happens in this system on times much bigger than 1 hour. Some guy will measure for 50 hours, maybe he will see some cutoff. We don't care. Because in this time scale, you need to ask, what is the relevant time scale? Let's say you want to use this blinking quantum dot for something. You want to use it for 1 hour. On this 1 hour, you have this power law, and this is going to be this with no characteristic scale, because this alpha here in this experiment is roughly 1/2. Between 1/2 and 0.8. Again, it depends on your system. It's a bit more complicated than what I'm saying, but it's always less than 1. So one can say, wait, you did this on and off times, but then you can say, why do I need to define this threshold on-off? Let's take a correlation function. And this is an example of an intensity correlation function. So you take 2 points in time, and this is the I here, this is the I here, the intensity, the number of photons emitted here, the number of photons emitted here. And you time average this, and you calculate the time average correlation function between 2 points in time. And this is what you get. So you get a mess. So if you had exponential waiting times on and off, and you do a correlation function, which is a time average correlation function, you'll see some correlation function that decays. And then you do it in one system, it will repeat. So this is just to say something very simple. If your typical time scale is diverging, the time average observables, correlation functions, intensities, whatever, they themselves remain random. So, and you can easily see this, but it's not the end of the world, because we can define theories slightly better than that. So before going on, I want to explain now briefly on this system what is weak ergodicity breaking. So again, I mentioned Bouchot said there is something called weak ergodicity breaking. What is weak ergodicity breaking in this very simple system? Let's say the system has on and off, only 2 states. You can break ergodicity in what we call strong ergodicity breaking or weak ergodicity breaking. What is strong ergodicity breaking? Imagine, this is not the case here, you add a quantum dots that if they start in on, they remain in on forever. And if they start in off, they remain in off forever. So depending on your initial conditions, you are either on forever or off forever. You have it, for example, in magnets. You know, at 0 temperature, all the spins are up, or all the spins are down. They are energetically the same thing, and what you choose either all down or all up, depending on some initial condition, like a toss of a coin. That's very typical in statistical mechanics. That is strong ergodicity breaking. What does it mean? Your initial condition, let's say you have a double well potential, and the well is the transition from one side of the well to the other is through a very, very steep barrier. So if you start here, you remain here forever. And you don't go to the other side, and then you don't have exploration of phase space. So strong ergodicity breaking means two things. You do not explore phase space. Your initial condition gives you where you are. And this is what people thought about ergodicity breaking long before Bouchot. But Bouchot said something else. Not on this system, but on glassy systems. He said, no, listen, look here. You have a transition from on to off, on to off, on to off many, many times. So how many times do you visit state on in this one long trajectory? Maybe thousands of times, thousands of jumps between on and off. So you are exploring phase space, and your initial condition, if you started here or you started here, there, is not important. In that case, by exploration of up and down, we are dealing with something we call weak ergodicity breaking. Why weak? Because you do explore phase space. You are both here and there. And that's why the breaking of ergodicity is weak. Why do you have a taller ergodicity breaking? Because the typical time scale diverges. So when you perform the time averages, you don't converge to the ensemble averages, but you do explore phase space. Now the fact that you do explore phase space, but the correlation time is gigantic, is very important. Why is it important? Because if you explore phase space, these two states, then you can build some statistical mechanics which is independent of the initial condition. So it's not that, oh, I started here and I'm doomed. You know, I was born in a small village somewhere in the earth and I'm going to stay there all my life. I do explore the world, and that means I can build some statistical physics, and that's what we're actually going to do now. So this is this idea. The strong ergodicity breaking, you have a phase space, and then you break it into pieces, and if you start here, you remain here forever. Weak ergodicity breaking, you are not decomposing. You can go from here to there, to there, to there, to there. However, you have power law waiting times in these individual substates, whatever they are. And these are so broadly distributed such that the mean does not exist. And then the system explores phase space, and then suddenly, if you look at it for some time t, it will choose one of the subspaces randomly, and it will remain there for something which is of order the measurement time. And then when you do a time average, it will not be the same as the ensemble average. That's the philosophy. So now I told you my main point here is not only to give you a small touch on what was done, but also to tell you really, guys, this is really common in some sense. So this is another example of an experiment. And this is a bead diffusing in a polymer network. The polymer network is actin network. The actin network is in your muscles. It's a very important ingredient of the intercellular outside the cell. This is important for muscles. So these are some polymers. And this guy, Weitz from Harvard, he wanted to investigate the diffusion of particles inside these polymer networks. So the polymer network is like some spaghetti soup, if you want. I think I mentioned it briefly before. And here you have a very small particle, and here you have a big particle. These are traces that the experimentalist puts in the system, and then they follow this tracer, and they want to see what is the diffusion. And they hope, oh, from this diffusion I can learn something also about the complicated polymer network, how it arranges, how it changes with temperature, things like that. So when you have a very tiny thing, all this is in water at room temperature, because cells, etc., are always at room temperatures. So, okay, this guy doesn't see these polymers and it just does Brownian motion. But when this guy is roughly the order of the measurement of the mesh size, big particle, this is roughly 1 micron, it gets stuck and then it jumps, stuck, jump, bam, 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 bam. It does a random walk with a lot of sticking times. which you can see in these trajectories. So again, this is taken for the laboratory. So sometimes the particle is totally localized in space. So this is 1 micron, this is x, y, and sometimes you jump a lot, but you see the time between jumps, this is one occasion of jump, puck, puck. So first of all, when I taught continuous time random walk, I said, let's say you have a lattice and you wait, and then you jump, you wait, and then you jump. Here you see the waiting and then jumping, waiting, then jumping, waiting, then jumping. But of course, when you are trapped in this localized trap, you also do some small vibration. I mean, you're not really standing and not doing anything, right? You are kind of trapped, so you have this noise and then you jump. And if you plot this trajectory, let's say the x trajectory versus time, this is 100 seconds, so you see this guy had many jumps. And then you can clearly see these jumps. And you can take this time, and this time, and this time, and this time, and that time, and that time, and that time, and that long time. And you can do it with many, many particles. And then you can plot the distribution of the waiting time from the data. This is what I call psi. And then, more or less, you see this is, again, a log-log scale, 6 orders of magnitude. Here we have 3 orders of magnitude, more or less a straight line. This is a guide to the eye of a real straight line. You can say, oh, not so great because there's some wiggles. Okay, you can do a better experiment, I'm sure. But the main point is that you clearly see, both from the trajectories and also from the data, you see most of the particles, or many of them, they jumped after less than 10 seconds. But some of them, after 1,000 seconds. You see the big scale, 1,000. It's a gigantic difference, and this is really an indication that you have no scale. What is nice here is that you can make the system that the average waiting time is infinite. But even nicer here is that you can control this slope. By making the particles smaller and smaller, you don't get this long track. So a small particle will be more or less exponential decay. This is for a particle whose size is roughly 1 micron, which is the same as the size of this polymer network. So you can control this alpha in this type of experiment. Now you can say, okay, this is a polymer network. He put in artificial traces, right? Something to follow. This is a famous experiment in our field. It's a messenger RNA diffusing in a cell. So this is coming slightly closer to biology. There is a but. It's not so simple. So here is the cell. It has a cigar shape. First of all, it's bounded domain because all cells are bound. And here you see the trajectory. This light here is this messenger RNA, and it's going and it's moving, and it's found. It explores phase space. First of all, it's easy to see that you are exploring phase space because you see you are here, you are here, you are here, you are there, you are in the middle, etc. Exploration of phase space. I'm not saying this is an ergodic process or anything, but you are not stuck somewhere. Okay? And then, so this you see here. So here you see, this is the cell, this cigar shape is the cell, and you visit more or less uniformly inside the cell. And these are trajectories. Maybe here you see long waiting times. I don't know, it's more complicated. I said there is a but. You see, and this is something maybe some of you, if you go to experiments, one day can solve. What is the problem? How do you follow a messenger RNA? You put on it some labels that emit light. It's like you have a car and you need something to emit light. So some headlights. So the first idea was, let's put quantum dots. You put one quantum dot, assuming the messenger RNA is much bigger than the quantum dot. The quantum dot will emit light. And then you can follow the messenger RNA in the cell. That was the idea at the beginning. That's why people, for example, looked at the quantum dots. But that would be very, very bad, because if you put one quantum dot on this messenger RNA, it will blink on, off, and then suddenly it will be off, and you will not see this. So how do you follow this in this? This is already an old experiment. You have this problem of blinking, power law blinking, which is horrible because you are dark for so long. So what do? One of the reasons is that they add more than one molecule emitting light to the messenger RNA. That is, of course, for biology is very bad because they are modifying the messenger RNA. It's the same size of a messenger RNA, but they put on it many molecules to see it. The molecules are the guys who are emitting light. And if you have, let's say, 10 molecules here on this object, okay, some of them are going to, they are all blinking. But you don't care because one of them blinks, goes off, okay, the other one went on, and you see it. From physics, you don't care, but again, from biology, you do care. That's why this experiment, which is beautiful, is published, for example, not in Nature, but in Physical Review Letters, because it's not real biology. It's very close. You take a molecule of the size of a messenger RNA, but you spoil it with too much light. Why? Because you cannot solve the problem of the blinking of the light emitters. So there is a gigantic effort to make smaller and smaller molecules that don't influence the motion of the messenger RNA, but still emit light, and that they are stable, they emit light forever. And this is very, very difficult for chemists, for biologists, for people who are interested in optics. And again, there are many hundreds of groups trying to solve these type of problems. In some cases, for example, in Ivan Garini's group, you can be extremely lucky. Sometimes your molecule that you want to follow has something that emits light in a natural way. Something called green fluorescent molecules, for example. And then you can follow the molecules perfectly without disturbing them from the outside, except for the laser. Okay, that's also a different issue. You need to work with low laser. Low laser is also a problem. Why? Because usually when you do spectroscopy, you work with low laser. Why do you work with low laser? Let's say you want to measure hydrogen atom levels. You work with low laser because you want the laser not to influence the atom. But if you have one molecule that it emits and you want many photons to come out, you need strong lasers in order for many photons to come out. But if you work with strong lasers, you heat the system. So there's always a trade-off. So I'm trying to say here, experimentally, these things are still, I would say, still people are fighting to get better and better experiments. This is something really big and gigantic in the context of how do molecules making life, how they move. That's the basic question. There's a huge, I believe still today, challenge because of optics, because of many things. But again, we can see more or less the motion of these objects and say something on the diffusivity. Okay, and then you measure the diffusivity. Okay, what's the diffusion constant? And what do you get? You would expect maybe you get Brownian motion. No. And this is the experiment. So what they measure here, this is the time average MSD versus this lag time. So if you are Brownian, then you expect that the MSD, the mean square displacement, grows linearly in time. And first of all, they take the molecules, they put it in water, and when they are in water, the MSD grows linearly. This alpha means that mean square displacement goes like linearly with the lag time, like Brownian particles. And then they put it in the cell, and then this is what they get. Again, this is a time average of individual trajectories. They see two observations. These are related to what I already said. First of all, the diffusion is anomalous, because this slope, this is again a log-log scale, this slope, you see, this is a guide to the eye, is smaller than this slope. And the MSD is increasing like subdiffusion, like t to the power 0.7. But in addition to that, each trajectory, the time averages, they're more or less parallel one to the other. But the time averages are random. You measure here, you get one result. You measure here, you get a second result. You measure here, you get a third result. In contrast, if you measure in water, and you measure for long enough, each time you will get the same curve. So you see, when you are normal diffusion, the time averages converge. They are reproducible. They are the same as the ensemble average. When you are doing anomalous diffusion, in the cell at least in this experiment, but in many others, the time averages are simply, each time you get a different result. So it's like you go and do an experiment, you do a time average, we believe it's long enough time, you get one answer, then let's say the first experiment, student gets this result. Professor wants to publish, this is the diffusion, we can calculate the diffusion constant out of here. Let's publish a paper. It's not, but then the student goes and the next day he performs another experiment and then you get this result. So the diffusion is this slope where it meets this line. If you think about a log-log scale, log of, let's say, 2 dt, so this crossing of this vertical axis is the diffusion constant, and this is showing that it's normal. You see that the diffusion constant is random. It's not reproducible. It's surely not ergodic, because each time you do a time average, you get a different result. Now, it's very difficult to say what are the reasons for that. Is it because they measure the same messenger RNA, but maybe the cells are very different? Is it because of some weak ergodicity breaking? Is it because of disorder in the cells? It's difficult to say. But we can at least analyze things in models, and we can make predictions. After the break, I'll come back and I'll show you the predictions, and we will see how we can test weak ergodicity breaking. The idea was simple. Here, what they are changing is the lag time. We are going to change, instead of the lag time, we're going to change the measurement time, the total time that you average over. And you will see that has a big effect, and that can be measured, and then you can say, oh, this or that experiment is falling in this weak ergodicity concept by not changing the lag time, by changing the measurement time. The brief reason is like this. You have these power law waiting times. Then you measure, let's say, for half an hour, and you explore traps of certain lengths. But if you measure for even longer, you'll find a trap that is even deeper. You get stuck for longer and longer and longer times. So how long you measure is also important, not only the time difference between 2 points in time. This, again, we will come back to this. Let's have a break, and then I'll come back to this after the break, okay? But this was kind of a brief showing you how this is related to experiments, without analyzing, without explaining the experiments even. But you see one thing for sure, that this anomalous is living, and it's very normal in some sense. In some sense, anomalous diffusion is now normal. It's simply common. Okay, so your final homework is titled on my webpage is Continuous Time Random Walk. There are 5 questions there, but you should answer only 4, the first 4. It's more or less, you need to re-derive the results that we had in the previous class. So it's just some summary of what is actually needed to understand the continuous time random walk of the previous class. So, and that you should hand in, but precisely next week on Sunday. Again, I checked on the webpage. You also have the midterm project. So again, choose one of the projects for yourself in order and present it to me next class. So everyone will have some project that he can focus or she can focus on during the break, and then I can give you some grade. But for now, we are going to do 2 things. I want to first present to you a theory, and then come back again to experiments. The theory is general, and it deals with following question. In usual statistical physics, we know that the time averages are equal to the ensemble averages. I showed you already that when you have these power law waiting times, this is not true. And this is, again, actually it's pretty obvious. It's because you have a diverging length time scale in the problem. It's not the same. On the other hand, we said, you know, following Bouchard, that there is some concept of exploration of phase space. So that there exists some type of statistical physics. I'm not explaining what do I mean by some type. This is actually the subject now. The question is, how do you formulate the statistical physics of weak ergodicity braking of these processes where you have these power law waiting times? And this is what I'm going to do now. So the first, when I say statistical physics, I assume or I postulate that the main issue in statistics, one of the main issues is people go to the lab, they measure time averages, and they want to replace them with some form of ensemble average. So let us discuss what is a time average in general. This is very general setting. So one aspect of time averages is so-called occupation fraction. Occupation fraction is, I imagine, a system which has states. These states can be many, many different things. For example, in the blinking counter dot, it can be up and down, 2 states. It can be in Boltzmann's statistics. It could be position in space, x. Think about it as discrete states where I bin the system. And I have I have a trajectory, and then I define the occupation fraction as the total time I spend in this state x divided by the measurement time t. The total time means, let's say you have, can you see this? Let's say you have Brownian motion inside a harmonic potential. It's a thermal system with temperature T, if Boltzmann holds. So let's say I look at this part of the system and I ask, how much time does the system stay here when the path is very, very long? So how much time it stays here? It comes in, it goes out, it comes in, it goes out, it comes in. It's like how much time you spend in this classroom. You come back many times. And if you have a long enough trajectory, and if you are ergodic, and if the system is bounded, then you will come infinitely many times in the limit of long time. And then you ask, this is the total time, Tx divided by T. And what is the idea of statistical physics? We do some time average. And this is denoted by this bar. What is the time average if you think about it? In general, it's some observable, Ox, which depends on the microstate. Here I sum it from minus L to L. This is just some notation. This will be a box over the times the occupation fraction. Because this is the meaning of the time average. You take the value of the observable, you multiply it by the time it spends in that state, and eventually you divide by the measurement time. You take the measurement time to infinity, and then you get the time average of your observable, whatever it is. So Ox, for example, if you measure, if I is the intensity of a quantum depth, Ox roughly is in the state on 1 intensity, and the state 0, it's 0. So this goes 1, 0. But if it's the position of a Brownian particle, for example, again, so you have x times occupation fraction px. And what is the idea of statistical physics? Let's replace this time, this fraction, by what? By the probability. That's why I have px. You replace this by the probability of the ensemble to be in state x. For example, this could be the Boltzmann probability if you are in equilibrium. And then, so what does it mean? That this occupation fraction in the different microstates of the system, in the limit of long time, it goes to, it has a distribution, but in the limit of long time, this occupation fraction goes to a delta function. The distribution of this goes to a delta function centered on the probability. And then you just need to replace these occupation fractions with probabilities. And then you have the usual statistical mechanics, because if I have here a probability, Px, then the time average, Ox, times peaks, the probability is simply the ensemble average, right? Okay, so this is the key issue of statistical physics in this talk, at least. Got stuck. Power law waiting times. Okay. So, to be slightly more specific, I'll give you an example that you know. So let us consider again the continuous time random walk. And let's do it on a lattice for simplicity. No external force. We can add these forces and they're actually super interesting. So we have a lattice which stretches from state minus L to plus L. So the total system size is 2L. And the dynamics is something like that. You start, let's say, here. You have a waiting time PDF with a power law waiting time. You stay here, and then you jump, let's say, to the nearest neighbors. But it can be anything. Any rule of jump is not important. You can jump from here to anywhere with some probability. We can make it much more general. And then you wait, and then you jump, you wait, and then you jump, and then you're drawing this power law waiting times. So for a quantum dot, you'll have only 2 states. In another system, let's say the polymer network, you have many states. The transition probability is, if you jump only with probability half, we call this unbiased random walk, except of course for the boundaries. Whatever the microscopical rules of jumping, we will try and treat this in generality. Wait, what's going on here? So, how does the trajectory look like? This again, I showed you similar figures. So, this is a simple kind of continuous unbiased random walk, and you have cell numbers here, -4 to 4. Just an example. And you start somewhere, I don't remember where, and then, okay, here you see I stayed in state 2 for a relatively long time compared to the history, then again and again for some reason, and then here, and then, oops, here I stayed long, and then here I got it long. I got stuck here. And this is a typical trajectory, and you see these power laws. The alpha here is equal half. So you see, as time goes by, like the thinking quantum dot experiment, the waiting times become bigger and bigger statistically because there's no typical scale, so there's no average, it doesn't converge, and the meaning of no average means that these waiting times become bigger and bigger as time goes by. On the other hand, like Bouchot said, you explore phase space. How many times did you visit this cell or this cell? Many times. You explore your phase space. So this is the trajectory. Now I can take this trajectory, or many other trajectories, and I can calculate the occupation fraction, which means I look at this cell, I calculate how long did I stay here, how long did I stay here, how long did I stay here, from time 0 till the measurement time. Just measure it. And here I show you the results for some trajectory, it doesn't really matter. This is when we chose the power law waiting times with alpha equal 2. And remember, what does this mean? It means that the average time between jump is finite. So this is normal behavior. You see, all the cells are the same. This is equal probability to be in all the cells. There are tiny fluctuations, if you see here, because my measurement time is not infinity. The occupation fraction here, etc. is the same. I have 9 cells. Occupation fraction is roughly 1/9. What is the probability to be in each one of these cells? 1/9. If I had many trajectories and I just counted after some long time how many guys are in this cell, this cell, this cell, it would be 1/9. But now here I take one trajectory, I simulate it, and you see I get this type of shape. So the occupation fraction is random. Now you see this landscape, it's random. Of course, if I make the measurement time bigger, then suddenly I'll get stuck in another cell, and then this will change. So this is not converging to anything. It's a total random landscape, and because these occupation fractions are random, also the time averages are random. But there is a relation between them, between the random occupation fractions and So now we want to quantify slightly better what does it mean, weak ergodicity breaking. We can think about dynamics not in real time, but in the number of steps. So n is the number of steps. So what is the probability to be at x at step number n plus 1? We don't care about the time elapsing here between step n and step n plus 1. It's simply given by some probability of jumping left q from x plus 1 to x, and probability of jumping right from x minus 1 to x. Here I assumed you jump only to nearest neighbors, but you can jump wherever you want. You can make it more general. And here in the previous example, this q was simply half. You jump to nearest neighbors with probability half, but in general, you have some probabilities. What are these probabilities in physics? These actually depend on the force and the coupling to the heat bath. So in general, there will later become a method to introduce the potential, etc., because we want to compare this to Boltzmann. But the main point, and maybe if you want the definition of weak ergodicity breaking, that in the steps, you don't care how long you stay. If I take n to infinity, there is an equilibrium of this guy, which means that after when n is large, the probability to be at x after 2 billion steps is the same as the probability to be at x at 2 billion plus 1. In this world, in number of steps, you are equilibrating. When is that happening? When your system is finite, of course, the usual type of ergodicity. You can say this in another word. This dynamics is purely ergodic in n steps, in the steps, not in real time. It's totally normal, provided none of these q's is equal to 1 or 0. Then you explore your phase space. If one of them is 1 or 0, then you get strong ergodicity breaking. If your phase space is one-dimensional, you split it into 2. So I assume all these q's are not 1 or not 0, okay? So then you have ergodic in n, and actually the time average is, if you, instead of time averaging, average over n, you'll get the same thing as usual ergodicity. So the idea is the following. How do we go back to real time when you do the time averages? So here, this is a cartoon. I'm just saying it very quickly, but you saw something slightly similar, so maybe you appreciate it, maybe not. Let us say the following. We have different cells labeled with x position. So nx is the number of times, it's an integer, the particle visits site x. For example, in a quantum dot, I had 2,000 transitions, 1,000 in up, 1,000 in down. Of course, we want to take n to infinity when the total number of jumps is very big. Only then you expect any type of statistical mechanics where you forget your initial condition. And then what we know is that nx divided by n, the number of jumps, is the ensemble probability, the probability to be in equilibrium at state x. This is important. Usual ergodic statistical mechanics. So you see this is actually, I'm replacing the occupation fraction by something called the visitation fraction, how much time I visit this place. But in the laboratory, what you are interested in is not in the number of visits in some state x, but in the time, the total time you spend in state x. So what is this total time? According to this kind of model, you visited nx times. Nx is now big in the limit when n is infinity. You each time came back, and then you draw your waiting time from a power law distribution. So the total time you spend in state x is the sum of IID random variable, whose mean is infinite because of the power law waiting time. And how many sums do you have? Nx. So if I want the distribution of the time I spent in state x, it's Levy's law. Because this is a summation of IID with diverging first moment. And this Levy law is given here, and this is something you should know from homework or from the previous classes. This is the one-sided Levy distribution with a power law tail that goes like Tx to the minus 1 minus alpha. So, of course, we have power law waiting times, and then you have also power law waiting times for this, but this is much more a stronger statement because it tells you the full distribution of these waiting times. And it's like a central limit theorem. It's like the Gaussian central limit theorem, but it's not Gauss, it's Levy. Levy is behind all the trick. And alpha is known from the waiting time. You have this amplitude A. A is the prefactor of the power law waiting time distribution. And here I'm writing down, I'm using this equation, how many steps you have, nx. That is n times px equilibrium. So here enters the number of summons, enters the ensemble equilibrium. What does this number mean? If you remember, when you have these Levy statistics, like the Gaussian statistics, it scales with n to power 1 over alpha. So this gives you how broad you are. This is the exponent of the power law. So how many summons do you have? If you sum, if px is small, then nx is small, and then the distribution is not so wide. If px is big relatively to other positions, your distribution is wide. So this is just a scale of how fat you are, like the scale of the Gaussian, but this is, again, a scale of the Levy. And now the idea is the following. What is the occupation fraction? How much time do you spend in state x? This is the time you spend in tx, divided by all the other occupation times. So I need to sum from minus L to L. This is what? This is simply the total measurement time. I stayed in state 1, 2, 3 different amounts of times. The sum of them is the measurement time. So what is happening here? If alpha is equal 1, that's usual statistical physics. What is this Levy function? It's a delta function. And then you get this px is going to be on this ensemble average px. But in general, if alpha is less than 1, tx is random, and you have this thing. Now comes a little bit of math. It's not trivial math, because you see what is happening here. Here I have a Levy, here I have a sum of Levies. Because this occupation fraction is, of course, between 0 and 1. You cannot occupy state x more than the measurement time, and it has to be bigger than 0, less than 1. So this random variable is not a power law distributed. It has a distribution, but it's limited to a domain from 0 to 1. But using the fact that you have here Levy for this guy and Levy for all the sums, we could show, I'm not showing you this. This is the kind of general framework of this field. So we have this time average, and it's given by this occupation function divided by times OX. OX can be many things. And your observable also can be many things, because one guy measures MSD, one guy measures whatever they want to measure, they can measure. The number of observable is really broad. But there exists a distribution, a PDF of the time average, and it's given by this formula. So in the limit of long time, this time average is random, because you choose randomly one of the states of the system. So when you repeat the measurement, you get random distributions for the time averages even in the long time limit. And I'm just showing you the results. So we understand certain limits. If alpha goes to 1, which means you are ergodic, you're back to usual Boltzmann-Gibbs statistical physics, you use this formula, and then you get the delta function is the distribution of the time average is the time average times the ensemble average, minus the ensemble average, which means the time average is equal to the ensemble average, as you know, as you were taught always. What does this equation tell you? Without the derivation, it tells you the following. You need to take this strange epsilon to 0. This is because we work in double Laplace space and we invert it. I'm not going into the details. But then you have here, what you see here, this is important, we have the probabilities of the ensemble to occupy state x. You have the observable at state x. This is the random variable. And And here you have this alpha. So for example, if alpha is equal 1, this guy is equal, this guy alpha minus 1, this is something to the power 0, this is 1. The sum of the probabilities is equal 1. That's by definition of normalization. And then you have this thing downstairs only. But here, when alpha is 1, then you see px times ox is the ensemble average. And sum of px, which multiplies the random variable, is 1, normalization. So what you have here is 1 over the time average minus the ensemble average plus I epsilon. That is, by definition, when epsilon goes to 0, a delta function. This is how you get this. On the other hand, when alpha is 0, going to 0, very small, what does it mean alpha goes to 0? You really get stuck in one state for really all the measurements time. It's very close to strong ergodicity breaking, but not exactly. Then this is 0, then this is 1, and then here you have minus 1. So this guy here is a delta function. And then you sum over all the delta functions, and then you get this guy. Which means the following. It's like you prepare your system in your states with some equilibrium probability, and then the time average is equal to that value at this particular state. Again, this is somewhat similar to strong ergodicity breaking, but there's a subtle issue on, first we took the limit time to infinity, that's why we got this equilibrium, and only then alpha to 0. So this is also a beautiful result because it does not depend on the initial condition. So for example, this is the most basic problem in physics. This is a particle in a box. You have this continuous time random walk. There are many states here. So you see it as a continuum. I take the box and divide by L. This is the size of the box. It goes from -half to half in this example. And then I do a random walk in the box. And first I choose alpha equal 1. And the particle is moving inside the box, collides with the walls many times, and then you calculate the time average of the position of the particle. So if I'm in this box and I do a random walk and I do a time average, on average I'm in the middle. Trivial. And I do it one time, I get one result. I do it the second time, I get the second result. And if I have a distribution of this time average, it's a delta function. This is this peak. This peak is on the ensemble average. On average, I'm in the middle of the box. But, and this is true for all the cases, but let's say the blue line is when I take this limit alpha going to 0. So I have here power awaiting times. And then I stay in one state, wow, nearly for the whole measurement time. This goes to infinity. So sometimes I stay here, sometimes I stay here, sometimes I stay here, etc. So when alpha goes to 1, to 0, goes to the strong ergodicity breaking limit, all states are equally probable, and I stay there forever. Wherever I'm born, I stay, and then you have a uniform distribution of the time average. Sometimes I started here, I remain there, and it's equal probability. And then when you change alpha, then you go, this is 0.8, so you have some width, because you are approaching the ergodic limit. And then when alpha is small, 0.2, you have this non-trivial shape. This one. This is, of course, only an example, because we can look at many systems, and this is just the simplest example you can imagine. And this is much broader than this very specific case, and it is related to these blinking quantum dots and to 1/f noise. And then the question is, how do you generate it from deterministic models, from chaos, disordered systems? It goes on forever. Because essentially all statistical physics can be generalized. So again, going back to a specific system, these are these blinking quantum dots. Wait 1 second. So again, we have this two-state blinking quantum dot. So we work with some experimentalists, and they can measure the time average of the intensity, for example. We thought it's easy, it's not so easy, as usual. So the time average of the intensity will be, the observable is intensity. You have two states. I can use that general formula to predict the distribution of the time average. What will happen? Sometime, if they are parallel, both and on and off, sometimes you are off for very long times. In other cases, you are very much in the on state for very long. And then when you do the time average, no matter how long it is, at least within some window, each time you do the time average, you get a different result for the average intensity. And this is just to say that there are many groups that measure these type of things, and it's really some kind of universal behavior. So the different systems, these are the quantum dots, cadmium selenide, this is the capping, different radius, different temperatures, high temperature, low temperature, some of them without capping, some of them with capping. I'm not going into the details. These are the exponents, 0.5. This is an exception because it has no capping. But these are what people reported. What is this alpha? Alpha is roughly 0.5, but then if you go to high temperatures, there are variations and people fight. Is it 0.8? Is it 0.5? It's important, but not so important, at least to my mind. It's not, we don't know exactly what is the exponent, but we believe it's something between 0.5 and 0.8 because it can depend on the system, etc. And very briefly, the physics is what we believe. And actually, no one really knows if this is really the physics. It's divided into two theories, one for uncapped quantum dots and one for capped ones. But I'm not going to go into these details. The essential issue is, people believe, and there are some measurements that indicate this, that why do you see ergodicity breaking, weak ergodicity breaking? It's because these quantum dots can be in a charged state and a neutral state. That's all. So on-off with power loss corresponds to charged quantum dot, you are off, dark. Neutral quantum dot, you are on, you emit light. And when you go from these two states, you go from on to off. The physical idea is the following, that if you are charged, then you come with a laser, you excite an electron hole. Instead of it emitting a photon, it can dump its energy on the other charge that is left here. This is called the Auger process. It's kind of known. So the line of thought here is that, you know, this ergodicity breaking may be related to some very simple process: charging, discharging, charging, discharging. The question is, why do you get power loss out of that? That is more complicated. But this possibly is related to the fact that when you get charged, you have an electron outside, and then it comes back with power law waiting times, like what we studied in one dimension. It's much more complicated because of the attraction of this charge. This guy is attracting it back. And this makes it kind of a one-dimensional problem. But this is a speculation. No one really knows until these days why do you get power loss in this system. It's debatable. But we can measure, for example, time average intensities. Unfortunately, so these are measurements, and they're done for 36 seconds, 360 seconds, and 1 hour. And the point of these experiments is just to show that the time average intensity does not go to a delta function. It's very wide, it's very wide, it's very wide, and maybe you can say maybe now it's starting to become less wide, but I'm not sure. Unfortunately, these experiments, they did 500 quantum dots. When you do only with 500 quantum dots, you have a lot of noise. So this is this noise. So here we repeated the model without the exact theory, but just by simulations, simple simulations. And you can see that these fluctuations are because the number of quantum dots is only 500. It just means that when you sample from 500 quantum dots, you have statistical fluctuations. The problem is if you measure one quantum dot for 1 hour, the measurement is 500 hours. So it's not so trivial for, I can tell the experiment, why don't you measure 10,000 quantum dots? To take them 10,000 hours. Now, that was true 10 years ago, so today people can really measure much more because they can measure in parallel, and hopefully they can gain better statistics, but the message is very simple. In real life experiments, statistics is highly non-trivial. To get these good enough statistics is a battlefield that's why I don't want to be an experimentalist. So what we kind of saw, and I'll talk about the last, just as a brief summary. So roughly speaking, you see this Boltzmann-Gibbs, all this idea is related to normal diffusion. In what sense normal diffusion? First of all, it's related to the Gaussian center limit theorem, which mimics normal diffusion usually. And these two, Gaussianity and normal diffusion, will lead you in many cases to Boltzmann-Gibbs. However, weak ergodicity breaking is also common, and then you have anomalous diffusion. The MSD goes like T to some power alpha. And instead of the Gaussian central limit theorem, we have the Levy central limit theorem. The Levy central limit theorem is important, as I showed, because of the occupation fraction. And then, usual ergodic statistical mechanics, you have this time average equal ensemble average. And here you have the more general formula. I mentioned briefly, but all this, you say, okay, these are stochastic models. Now you want to build microscopical, dynamical models, deterministic models with no noise, with no assumption of power laws. So usual chaos, which means that the separation of trajectories is sensitive exponentially, can be shown to lead to usual dynamics. But there are some systems which have zero Lyapunov exponents. I don't know if you know what it means, but if you are interested, we can discuss later. This is sometimes called weak chaos. You have some randomness, but it's not exponential sensitivity. And this leads to something else, which is called the infinite invariant density, which this is what I dealt with in the last 10 years or so. And this is an old story, weak ergodicity breaking. Now we are treating this infinite invariant density, which is a whole new interesting field I'm not going to discuss. What I do want to discuss is you see, all this is Boltzmann-Gibbs is in equilibrium. Boltzmann-Gibbs is when you have a finite system. But, as I mentioned already, you can measure also time average MSDs and say that they are the same as the MSD, for example, for Brownian particles. Single particle ensemble, they are the same. In our case, it's not surprising that transport coefficients, what do you mean transport coefficients, like the time average diffusion constant, they are also going to be random. But we can quantify this, and this was done extensively in my group and other groups. And now I'll just briefly discuss it, and this we can also compare to experiments. Okay, so again, I just go back to remind you, we have the following. Now we have an infinite system. This is a very easy exercise, actually. You take the continuous time random walk with power law waiting times, and you simply measure the time average MSD. As a function of delta, for some measurement time, the measurement time is big. And you see this, you see, first of all, randomness of the time average MSDs. This line is the average over all of them. And you see the slopes. At first, this was the reason why we did this. This is similar to what you saw in the experiment in the cell. In the experiment in the cell, you saw Golding and Cox. They take the time average MSD, they measure mRNA, and they see randomness. Here I choose alpha, I don't know, let's say 0.5. If I choose alpha, if I did it with alpha bigger than 1, let's say 3 or 2, all these lines, all these red line and blue line, they will go onto one master line. So there is a distribution of the diffusivities. Sometimes you go relatively fast here. Remember, this is a log scale. Sometimes, like here, you go very slow. Why is that happening? Because on the measurement time t, this guy happened to fall into a very deep trap and barely not move. This guy didn't experience much traps and moved a lot. So the time average MSDs are very different. But the nice thing is you can look at the distributions of these continuation, the distribution of diffusivity, so to say. And also you see that these lines are more or less parallel, which means that from a single trajectory at least you can estimate is the diffusion normal or not. Let's see the. First, I'll just give you the statement of the. What does the theory predict? So again, the theory we use the continuous time random walk with no boundaries. We start somewhere and we calculate this time average MSD, and now you saw it's random variable, so we average it over many trajectories. That's the black line I showed you before. And the final result is interesting. There is some d alpha. This is some like a diffusion constant, but it's anomalous. It depends on this alpha. It's linear in delta, but it ages. It goes like t1 minus alpha. So this is super interesting because it means that the ensemble average goes like t to the alpha. So the ensemble average is anomalous. But with respect to the lag time, this is perfectly normal. Where is the anomaly? The anomaly is downstairs here. See, t1 minus alpha. So if alpha is half, you have a 1 over t to the half. What is up? And this effect is called aging. The older you are, the bigger t is. Delta is fixed. The slower you move. We know this. You know, young babies, they move fast. Old people move slow. So the older you are, you move slow. If alpha is 1, 1 minus 1 is 0, and then you don't have this aging. And then this diffusion constant is simply the usual diffusion constant. So what is happening here, roughly? The time average MSD, when you are normal, is 2 times d times delta. That's Einstein, Perrin, Langevin, all these things. What is the diffusion coefficient for anomalous diffusion? You have the derivative of x squared dt, that's t to the alpha minus 1. Because x squared is t to the alpha, so this is t alpha minus 1. Very easy. So, you see here, I just replace this d by this time-dependent diffusion coefficient, and I get this. This is not a mathematical explanation, but this gives you a taste. What it means is the diffusion coefficient in some sense is changing. Alpha is less than 1. You move slower and slower as time goes by, and then you get this aging effect. Now, this is what I referred to previously. This is something that you can measure. What do I mean measure? You have thousands of laboratories around the world. They measure MSDs. They measure diffusion constants. And they will always plot to you delta squared, the time average MSD, versus delta. They never, as far as I saw, until we told them to do that, they never change the measurement time. They just take the longest measurement time they can, and they measure. And then they might find normal diffusion. So we just, told people, you should also change the total measurement time. And you will see this aging if all what I told you is correct, and we'll see this in experiments. This is only a small part of the theory, because this creates a problem. What is this delta? For example, in Golding and Cox, there was no delta here, it was delta to some power. So I'm not going into that direction, but you remember in Golding-Cox experiment, the system was finite. And it hit the wall many times. This actually modifies this law. So this law is valid only for an infinite system. And you also assume here that the jumps to nearest neighbors are like a usual random walk. So this can be changed by changing the rules of diffusion, and there's a lot of work on this. We're not going into these details. We are just the simplest model. But this just gives you the average of the time average. Again, the time average is random. This delta squared is random. This we calculated by averaging over many trajectories. Now we can define a random variable psi, which is the time average over the MSD, mean square displacement, over its corresponding ensemble average. So this psi on average is equal 1. And it has some distribution. And the idea, and this distribution is something you know. The idea is the following. The time average MSD, no matter what, if it's normal diffusion or anomalous diffusion, within this continuous time random walk is proportional to n. N is the number of steps of the random walker. So the idea is, if n is usual normal processes, what is n? It's simply t divided by the average number of the time between jumps. And then you get normal diffusion. That means delta squared, simply the lag time divided by the time between jumps. That's Einstein's theory. But in general, this n, if you have these parallel waiting times, this n is random. And then what we are saying here is this psi, this random, normalized random variable, which has no units, and its average is 1, its distribution is like n divided by average n. And the distribution of n is something you know. This is the total number of renewals between time 0 and time t. This is what I call the inverse Levy distribution. We calculated it when we calculate the number of steps in the random walk, or the continuous time random walk. So again, you see here Levy. So this is the PDF of psi. It's given by the PDF of the number of jumps within the time interval. And it's given by this Levy function, again, which generates the number of steps in the random walk. And this has the following behaviors. For example, when alpha is equal to half, it's a Gaussian. So it's half a Gaussian, but of course this psi is always bigger than 0 because it's a mean square displacement. So this Levy distribution where psi is 1 over psi to the alpha, if you put your alpha equal half, this Levy goes into the Gaussian. This is some simulation, and when alpha is 0.75, it looks something like this. And what is this peak? When alpha will be 1, you'll have a delta peak. That will be time average equal to the ensemble average. You see this law is not the same as the law I gave you before in equilibrium. This law is related to Levy and the number of renewals. It doesn't have in it Px, Ox, all this more glorious equation that we had before. This is a very simple equation, and it means the following, that you have time averages. But it depends what time average you look at, you have different distributions. You have a classification of time averages. Some of them follow this law that is also called sometimes the Mittag-Leffler law. I hate this word because it's Levy. And others are described by this formula I gave you before. And in that sense, it's an involved theory. It's not as simple as usual statistical mechanics where I say, okay, time averages, they're the same as ensemble average. That's a very easy statement. You see that the distributions are, you can quantify these distributions in a very neat sense. So all is well and good, but now the question is very simple. I told you before that there are many experiments in the cell measuring diffusion. Okay, so maybe a few of them at least would start checking this aging effect, and indeed there were roughly 5 experiments. After that, it's already difficult to publish, which did the following. They took the time average mean square displacement, and instead of changing the lag time, they change the measurement time. And you see this aging. This is real data. It goes down. And this is exactly what we predicted, that as time goes by, you get into deeper and deeper traps, and you slow down. And you see that the older you get, the slower you are. This is done for different lag times. So one experiment, this is, the lag time is small, so it's down here. And then this guy is the biggest lag time. So of course, when you increase the lag time, of course the MSD is growing. Just take 2 points, and the distance between them is bigger. So of course you diffuse more. But again, you see here very clear aging, which is a sign of non-stationarity and a sign of non-ergodicity. And of course, usual Brownian motion will never give you anything like this. This was done by an experiment by Diego Kraft from already 9 years ago, but he's working in Colorado. So all I wanted to emphasize is this is kind of related to real experiments. And of course, once you measure this aging, then you can say, wait, let's also measure the waiting time PDF, the waiting time between jumps, because the exponent of the aging is related to the waiting time PDF. If you know the alpha from psi of tau, then you know the alpha from the aging. They should be related. So of course, he measured also the waiting time PDF. And it's more or less a power law. You can see here very broad distribution. So it's another evidence that what is happening here is some trapping mechanism, that you fall into deeper and deeper traps, and they are power law distributed, at least for some time scale. So here it's from 0.1 second to roughly 1 second. So this is only 2 orders of magnitude. This experiment was done, it's very different than Golding and Cox. It was an experiment where they took the membrane of the cell and put on it some ion channel, and it was diffusing on the membrane of the cell. These ion channels are also important for everything because they transmit ions from one side of the cell to the other, and it's a gigantic field with Nobel Prizes. But these channels, they move and diffuse, and you can follow those channels in the 2-dimensional plane. So this was, unlike Goldie's experiment, this is a real system. There's no, we don't believe the optics is influencing here. This is really the ion channel moving, the way it's moving in a natural, most natural way. Well, again, in the first experiment, we had to add many molecules, and we were disturbing the experiment. So, of course, okay, this is a bit newer. For you, it's very old already, but there is advancement slowly in this field. Okay, so I think I'll leave you some references. You can, in principle, you can maybe use them also for work if you are very mathematical for your next, again, I repeat, next week, you should have decided which work you are, and you should talk to me. I would really appreciate if you come up to me, let's say, not today, not tomorrow, but let's say on Wednesday, and you decide. Inform me in advance, because if, for example, there are roughly 15 people or 20 people, if all of you decide to do the same project, then I will not agree. I don't mind if a few people do the same. So also talk among yourselves. And the people who will approach me first with one project, I'll write down their names on that project, and it's theirs. And if there will be 3 or 2 people, that project is ended. So I hope that you will have self-organization and that you will not choose the same project. But if you want to be secure, you choose a project and you come to me, and the guy who will come late, unlucky for him, okay? So these are just some references. I think they are, maybe some of them are on the list that I have. Again, the list is on my webpage. But the guy, this guy is a kind of popular review, but it's not really good to do a project from it. because it's too popular. If there is someone in the audience who's very much interested in chaos, so we can work on chaos. I don't know, maybe there is some nonlinear guy here. This describes the time average MSDs, this describes equilibrium. There are many more rocks related to fractional diffusion equations, fractional Fokker-Planck if you're more mathematical. All these time averages are functionals. The functional is you have a trajectory x of t. X of t is random. And what is the time average? It's an integral over an observable which depends on your trajectory. That's called the functional. So all this theory of distributions of time averages is actually a distribution of a theory on distribution of functionals. So there's a lot of work on this. These are the old works on blinking quantum dots. These are the old works on continued time random walks. So please think carefully what you choose and come back to me for discussion. Okay? Okay, so I guess I'll see you next week.